Section 5.5 Bases other than E and applications. Definition of exponential function to base A. If A is a positive real number with A not equals 1 and X is any real number, then the exponential function to the base A is denoted by a to the x, and it is defined by a to the x equals e to the power ln of a times x. The logarithmic function to the base a is denoted by log base a x, and is defined by log base a of x equals ln of x divided by ln of a. Differentiation and integration. To differentiate exponential and logarithmic functions to other bases, we have three options. One is to use the definition of a to the x and log of base a of x, and differentiate using the rules for the natural exponential and logarithmic functions. Number two is to use logarithmic differentiation that we studied earlier in chapter 5. Or simply, option number 3, use the following differentiation rules for bases other than e. So the derivative with respect to x, a to the x, equal ln of a times a to the x. Notice how similar it is for compared to the derivative of e to the x. It's just e to the x itself, and it's just a difference of the constant factor ln of a. Similarly, if you take the derivative with respect to x, log of base a of x will equals 1 over ln of a times x. Again, it's very similar to the derivative of ln of x, which is 1 over x, and we gain the factor of ln of a. Now let's take a look at the following two examples of how we can apply these formulas to find the derivative of functions involving exponential and logarithmic functions with base other than e. So example number 1, find the derivative of f of x equals 2 to the 3x plus 5. And we notice it's a composite function. It's a exponential function composed with the function 3x plus 5. So we know we will need to use the chain rule. The chain rule tells us the derivative of a composite function equals the derivative of the outer function, which is 2 to the 3x plus 5 power, because it's an exponential function with base other than e, is itself times the constant ln of 2. Then because of the chain rule, we need to multiply by the derivative of the inner function, which is 3. So to simplify, the derivative will equal 3 ln of 2 times 2 to the 3x plus 5 power. Now on the other hand, when we find the derivative of the function in example number 2, we notice we can also apply the chain rule. However, in this case, we're dealing with a quotient, and we would love to avoid quotient. So we will have to use the property of logs. Log of a quotient equals difference of logs. 5 of the numerator, square root of x. But square root of x is x to the 1/2 power. So we factor out the power 1/2 using the power rule of log. And we have to subtract the log of the denominator, x plus 5. Now once we simplify the function, it will be very easy to find the derivative applying the rules that we already know. Derivative of the first term, we get 1/2 constant remain. Log base 5, we use a rule for derivative of log base a. So we will have 1 over ln of 5 times the inner function, which is x. And then we have to subtract the second derivative of the second term, which is, again, according to the derivative differentiation rules. Again, according to the differentiation rule, we get 1 over ln of the base 5 times the inner function x plus 5 and times the derivative of the inner function x plus 5. Derivative is just 1. So the final answer would be 1 over 2 ln of 5 times x subtract 1 over ln of 5 x plus 5. Next, we will take a look at the most common application of exponential function in finance or banking. Example number 3. A deposit of $2,500 is made in an account that pays an annual interest rate of 5%. Find the balance in the account at the end of 5 years when the interest is compounded A. monthly and B. continuously. Now for part A and part B, we will have to use two different models, and which we have learned those formula in pre-calculus. So the future value in part A will equals the principal or the present value times 1 plus the interest rate divided by the number of turns or the number of times it compounds in a year raised to the n times the number of years. So in this case, in part A, the future value or the balance in the account at the end of 5 years will equal present value is $2,500 times 1 plus the interest rate is 5% and we change it to a decimal 0.05 divided by n is the number of times the interest is compounded in a year. Since part A is talking about monthly and there are 12 months in a year, so will n equals 12. Okay, raised to the nth power, n times t's power, n equals 12. T is the time in years, so times 5. Now you will need to use a calculator and input 2,500 times 1 plus 0.05 divided by 12 raised to the 60 power, and you should get approximately $3,208.40. We usually round money to 2 decimal places. So So that is the amount of money at the end of 5 years if the interest is compounded monthly. For part B, if the interest is compounded continuously, we will use a different model, which we also learn in pre-calculus. A equals P times e to the r times t power. And we will later on in chapter 8 learn about how this 1 plus r over n to the n times t power, how this limits because we're compounding continuously, so n equals infinity. How will this limit equals e to the r times t power? But for now, we can just apply the formula that we already know, that is moduling the interest for this problem. So again, P is a present value, $2,500 times E is just the number E raised to R is 0.05 times T is 5 years. Now use a calculator. Do you expect this number to be more or smaller than $3,208.40? That's right, the number should be bigger. We should get $3,210.06. Now notice that even though we compound continuously, the interest didn't grow that much more. Compare these two numbers. They are just like $2 difference.